Hey everybody, we're going to spend some time talking about the integrated rate law, and by the end of this video you will be able to apply the integrated rate law and understand when to use it in a kinetics problem. So here we have the interesting thing that goes on. The rate law, which I will write up here to remind people, R equals the equilibrium constant, or I always say the equilibrium constant. I don't really mean the equilibrium constant. The rate constant, let me just make sure that I can, equals the rate constant times the concentration of A raised to some power M times the concentration of B raised to some power N. And so what we notice there is that this doesn't have time directly as a variable. Yeah, time is kind of buried into the rate because it's change in concentration over change in time. But if we really want to know how the concentration changes over time, time should be a variable that we can change to figure out what the concentration is. And so this is important to know how long a reaction will actually take, or how much compound will be present after a given amount of time. Okay, and so these types of rate laws that are related to time, or that show the relationship of time to concentration, they're called integrated rate laws. Now, calculus is the way we get that. Instead of doing the derivative of the rate law, we integrate the rate law, and when we integrate the rate law, we have two rate laws that come to be. There's the first order and the second order rate law. And so first order rate law comes from the idea that there's just a 1, and that's the overall order, that the overall order of the reaction is just a 1. The second order rate law comes from this and this adding up to 2. So that means this could be 1 and this could be 1, or this could be 0 and this could be 2, or this could be 2 and this could be 0. But whatever, the overall order is 2. Now, of course, there's third and fourth and fifth and sixth order rate laws, and there's even 0 order rate laws. But what we're going to do is really talk about just first and second order rate laws. Those are kind of the two big ones to get the point across. Okay, and so this is the first order rate law. I'm sorry, the first order integrated rate law. Sorry about that. So this is the details of this is the first order integrated rate law. Okay, and so this is one form of it. We can rewrite this any way that we want, mathematically speaking. But this is the one that you'll see written down usually on your reference sheets. Okay, and so in order for us to understand it, well, let's see here. There's K. So K is the equilibrium, or is the, see there I go again, equilibrium constant. K is the rate constant. T is time. Okay, T and C, I always write T with, they call it a terminal, but I think dingus is a lot more funny. So I always write T with a lowercase t with a dingus. Okay, and this is the concentration at whatever time is there, and this is the initial concentration, which is something that we can measure. Rate constant is something we can calculate, and the time is something that we can easily measure, which will then allow us to figure out what the concentration is at that time. Or, thinking about it the other way, if we have a target concentration that we want to get to, we can then figure out how much time it's going to take to get there, provided that the reaction is first order. That's, for the first order, we're dealing with natural logs, ln's. Okay, so it turns out that the easiest thing to do is to rewrite the equation, okay, because a lot of kinetics is going to be graphing and understanding how graphs interact with the chemistry. It's just the way it is. And so here I guess it's not how graphs interact with chemistry, but it's how graphs can represent chemistry. Graphs don't really interact with chemistry. That would be weird. Regardless of that, okay, what we did is we just rewrote this formula, and we did it in such a way that it is now in the slope-intercept form in terms of y equals mx plus b, okay? And that's key, because if we do things correctly, if we do our chemistry correctly, and it is a first-order equation, again, this is a first-order rate law, the first-order equation will produce a straight line when we plot y, which is ln of a, versus the time, okay? And so that's kind of a neat check when we're doing our chemistry, okay? Now, and so I explain all of those things here in this slide, okay? Plot the points, if it's linear, it must be first order, okay? Now, the big thing is this one, okay? Oh, I'm sorry, not that one, okay? There's another point, and the point is what happens if you plot ln of A, concentration of A, versus time, and it is nonlinear, okay? Well, if you plot that and it's nonlinear, I know you're going to say, well, it's going to be second order. No, it's not that it's going to be second order. What we know is that it's got to be something other than first order, which means it could be second order, third order, fourth order, could be zero order, whatever. Okay, but if we plot ln of A versus t, right? If we plot y versus x, we should get a straight line. If it is not a straight line, okay, like this one is curved, then it's not first order. Okay, if it is a line like this red line here, the rate constant k equals, negative k equals the slope. How do I know that? Well, let's go back here. Okay, negative k is the slope. So we can use this to also determine what the rate constant is for this reaction. Okay, so that's good. Now, what about the second order rate law? Okay, well, the second order integrated rate law is written usually in this form right here. Okay, notice the difference. First order has ln, uses natural log. Second order is 1 over. Okay, and all the values are still defined the same as they were in the first order. It's just that the form is different. Different order means that it's going to be a different reaction. The concentrations are going to change the rate differently in a second order reaction. Okay, and so again, what we do is we rearrange this to give this form of the equation. Notice that this form of the equation again is in the form y equals mx plus b. Okay, and again, when we plot this and we get 1 over concentration of A versus T, and we get a straight line, that's how we know it's second order. If it's not linear, 1 over A versus T, we don't know that it's first order. What we know, it's just not second order. Okay, and I think that that's important. Okay, so and again, in this case, what's m? In first order, the slope was negative k. If it's second order, then it's not going to be negative k. The slope is going to equal k, no matter what. Okay, as long as it's linear. Oh, we're not going to do the Arrhenius equation. Not in this video, at least. I thought that there was one more slide doing sample problems. But at any rate, that's the integrated rate law, and that's how we determine how time and concentration are related to each other. I'll provide a little sample problem, and we'll go from there.